All right, so today's lecture question, the only thing that changed from this lecture question is that you do have to do testing now. So I added this test fib test class. So if you did download it early, there's no big lecture question change, but you do have to do testing in test fib. And I added a ceiling. Since you're writing test 2, it's before I just wasn't testing on inputs greater than 46. But now that you're writing testing, I got to make that explicit as well. Explicit. Don't test with any inputs greater than 46 or less than 1. So we're computing Fibonacci numbers. This is probably something you've heard of in at least 3 different math classes. Fibonacci numbers. If you haven't, Fibonacci numbers, it's a sequence of numbers starting with 1, then 1, and then every number after that is the sum of the previous 2 numbers. So we go 1, 1 is the base cases, the initial conditions, and every number is the sum of the previous 2. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, so on and so forth, out to infinity, out till forever. So our function treats the first Fibonacci number as 1, the second one is 1, so we're not indexing from 0, we're indexing from 1. And your goal is to write this functionality and then the test cases for it. Of course, this is a 115 level question as stated here. What makes it 116 level is var. We are finally banning var. You've heard about it for a while. It's a reality now. We're doing the thing. So you cannot use the keyword var. You cannot do anything that simulates a variable either. Especially for the homeworks, I'll be looking for the ways that you can simulate variables without using the keyword var. So none of that, like if you use a mutable list, or a list buffer or something like that. None of that either. So no var, which forces you to write a recursive function to be able to write this one. And as long as you're somewhat comfortable with recursion at all, this one isn't too bad. This is an ease into recursion. But it still makes you think about this new way of thinking. No var, write recursion whenever you're tempted to really use a var. So yes, we are talking about recursion. We're talking about merge sort today, which is the first recursive algorithm that you've seen back in 115. So let's get into it. No var, and that's going to be true for all the rest of the lecture questions for functional programming. No var, and of course the homework assignment, which I should have posted tomorrow. There's only going to be one homework assignment for this, and it's going to be the genetic algorithm, which you've probably also heard of from the TAs. I actually haven't even told them yet that it's only going to be one. So TAs, just one. Which I think the TAs will be happy for. They wanted everybody to do genetic algorithm. I gave an option last semester. A lot of people just didn't choose genetic algorithm, which is kind of sad because you learn a lot more, I think, through the genetic algorithm. So we're getting rid of that other option. Okay, so we've seen from the survivors. So we've seen selection sort last time. We've seen that it's very inefficient. You've also seen it in 115. Very inefficient algorithm. But let's be more specific about what we mean by inefficient. Let's pull out some big O notation. I believe you've also seen a little big O notation last semester too. So hopefully this is some more review that we can kind of slow down a little bit and digest some things. At least the first few slides of this thing. So big O notation. We measure the asymptotic runtime of an algorithm in terms of the size of its input. We name the size of its input some value n, and then measure how long that algorithm takes in terms of n asymptotically. We ignore all constants for this. We ignore all lower order terms, and we just want the magnitude, the asymptotic magnitude of that growth. So for example, if a runtime is O of n, and for sorting, n is the number of things that we're sorting, the size of the data structure we're sorting. And like, for example, a runtime of big O of n is going to be a linear runtime because the runtime is going to grow linearly with the input. This might be any linear equation. It might be 3n plus 6 or whatever, or a million n plus 8, 1/2 n minus 3. It might be any linear thing, but we drop all the constants, drop all the lower order terms, and just say it's O of n. It's linear. And that's all asymptotic analysis cares about, the asymptotic runtime. You can think of this as, if you think of it in terms of limit to infinity, O of n, just an n, its limit to infinity over it divided by the actual runtime, the exact runtime with all the constants. Take that limit to infinity, it's going to be non-zero, non-infinity. It's going to give you some constant that tells you that the runtime is exactly that runtime. You can say it's O of n because its limit, the limit to infinity of the division is non-zero, non-infinity. For those of you who want a little more calculus in your lives. If that explanation doesn't make much sense to you, don't worry, you won't really have to think about that till 250. I'm just giving you a quick sprinkling of big O notation today. So we looked at selection sort. This is the algorithm that we saw last time. Let's do a very quick runtime analysis of it. The outer loop here, we have nested loops. Our outer loop is going to run O of n times once for each indice that we're calculating. And then we have an inner loop. For each of those O of n times, we have an inner loop which also runs O of n times. It's going to run at worst case. We always think of worst case analysis. Worst case, I is 0 until the size of the data structure. That's n times that we're going to assign j some value and run through this loop. So this is an O of n loop. We have an O of n loop inside of an O of n loop. When we have nested loops like that, we multiply their runtimes, and we end up with an O of n squared runtime for this algorithm. And oops, actually, we get an O of n squared or O of n cubed runtime because of this specific implementation. Data.apply, the apply method of a list, is an O of n runtime method. And also, these swaps, since I have an apply out here, these swaps are going to be O of n time as well. So we have an O of n loop, which runs O of n squared work, and then O of n work. It ends up being O of n cubed, mostly because of this apply. If we could get rid of that and get this to be a constant time call, then we could get O of n squared out of this. So this is a very horribly inefficient algorithm. Very, very, very bad. Reddit, I'm not clicking that during lecture, but I'm curious what it says now. So this is a very bad, it's an inefficient algorithm and an even more inefficient implementation. Just want to point that out, that we have a bad implementation. More details on that, not next week. I don't know why this says next week, but in 2 weeks. I don't think I've ever done this within 1 week of the other lecture. But when we get to linked lists, that's going to be in 2 weeks. We're going to see why that's an O of n algorithm. It's a stats for a year ago in GA. Oh, when I did the emojis up on the projector. Oh, the good old days. I miss that. When part of my job, I made it part of my job to look at the homework results and decide which emoji perfectly captured my reaction to the homework results. That one was a very bad one. That did not go well. I'll let you know I did soften up GA a little bit. The homework isn't as difficult as it was that semester, but it is by no means easy, especially since you can't use variables. So let's do a little bit more serious analysis of that runtime. I said worst case O of n on that inner loop, but it's not actually O of n. If you're really watching that, you know that the first run is going to be O of n. The first time that inner loop for the first index, it's O of n because we have to compare every single element in the linked list. But like when we're halfway through the list, we're only doing n over 2 checks. When we're towards the end of the list, we're only doing like 2 or 3 checks, iterations through that inner loop. So what we actually have is n for the first iteration of the inner loop, n minus 1 for the second, n minus 2, so on and so forth, till 2 to 1. If we take this sum, we know that this is pulling out some of our mathematics. We know that this adds up to n squared over 2 plus n squared. And in asymptotic analysis, we're only concerned with the highest order term. So we ignore this lower order term, this linear term, only look at the n squared term. And we're also ignoring constants, 1/2 times n squared. The 1/2 is just a constant. And we still arrive at our n squared runtime. So if you're wondering, if you think I just pulled some smoke and mirrors and said, hey, worst cases is n squared, worst cases is linear, so I'm going to assume it's always linear and do n plus n plus n plus n plus n. That wasn't completely fair, but once we expand out the math, we still get the same thing. We still get an n squared overall runtime from that inner loop, even though every iteration of that inner loop, every time we hit that inner loop, it's not exactly n. It's still going to work out in the math. And we saw in 115, you very briefly saw, if they're even still showing in 115, I believe they are, but just kind of mentioning that merge sort exists and showing you the code and talking about the runtime of it without understanding how merge sort works. That's what we're here to talk about today. But you did see that we can get down to O of n log n, which is significantly faster. Log n grows extremely slowly. This is very close to being a constant without being a constant. It's a very slow runtime. So we're getting very close to linear, very far away from our n squared, very much more efficient than our n squared. So let's see how we got there. You know it's a recursive algorithm, but let's see how it works. So here's the whole algorithm description in one slide. The algorithm is one check. If the input has one element in it, return it. It's already sorted. There's nothing to do. Our work here is done. We got a list with one element. What do you want us to sort? What do you want us to do? There's no other possible ordering. It is already in its only ordering. It's already sorted. Nothing to do here. If there's more than one element, we're going to divide the input list into two halves, recursively call merge sort on each half, and then merge the two sorted lists together into a single sorted list. So if this thing isn't sorted, if I have a list of elements that's not sorted, I'm just going to chop it in half and call this same algorithm on each half. This algorithm sorts lists, so it's going to sort each of those lists. Once I get each half returned already sorted, my task is to merge two sorted lists, which we can merge much faster. We'll see how to do that as well. We can merge two sorted lists that are already sorted, much faster than we can merge two unsorted lists by taking advantage of that sorted order. This is the whole algorithm. There's nothing else hidden here except the details of merge. We'll talk about the details, but just assume that we can merge two sorted lists into a single list, and you can probably guess and come up with ways that you would do that if that were a lecture question or homework. But this is the whole algorithm. This is it. Nothing's hiding here. But it might seem, or at least I'll say it should even, seem like something's hiding because we're recursively calling the algorithm itself and just assuming by magic that it works. But we really haven't done any sorting yet. So how does this actually work? So let's see an example. Before we get into the code, let's see an example of what we even mean by this algorithm. So we're going to take this input, which is conveniently a size that's a power of 2, so it looks all nice and pretty on a slide. But I'm going to take this input of size 8 and call merge sort on it. When we call merge sort, the input size is greater than 1, so we're going to split it into two lists and recursively call merge sort on each list. Call the same exact algorithm on both halves of the list. And then when we call merge sort, it's going to do its only check. It's going to say, is this more than one element? Yeah. So break it up even more. Each call is going to break it up even further into half. Is the input size greater than 1? Yes. Break it apart again. On each of those 4 calls, now we have 8 calls to merge sort. And for these, is the input list greater than 1? No. So we're done. This list is sorted. This list is sorted. This list is sorted. This list is sorted. So on. We have 8 sorted lists, each with only 1 element in it. And our task is to merge these lists. So we've successfully sorted this list. The list of size 8, we sorted it, but we sorted it into 8 lists of size 1, which are all independently sorted. Now we have to merge them together to get the full sorted list of size 8. So to merge them together, we're going to, this call of merge sort, which is on the stack, we want to start talking about stack and heap again. This call that's on the stack, after these 2 calls return, its job is to merge those two returned lists. So we get two lists. We have the guarantee that both of those lists are already sorted, and we're going to merge them together into a single sorted list. So we're going to compare 51 and 1. 1 is going to come first, 51 comes next. This call is going to get these two sorted lists. It's going to decide 19 goes first, then 100 goes next. And same thing on the other side. We're going to get 2 and 8 and 3 and 4. Now this call of merge sort was waiting for both of these calls to return. Once those two stack frames return their values and say, here's two sorted lists of size 2, now we merge these ones together. We decide the 1 goes first, then the 19, then the 51, then the 100. Same thing on the other side, merging all these lists together. And then the top level call of this has both of these stack frames returning their values. We have two sorted lists of size 4 that we have to merge. We merge these things together and get all the values in the proper order. So a lot of the actual sorting happened from the base case just by saying it's already sorted. And then the rest of the work is done in merging two lists under the assumption, a very important assumption, under the assumption that those two lists are each already sorted. So here's the code. And of course we want to highlight the recursion. So merge sort, we're going to use the same structure that we used for selection sort last time. We take a type parameter t. So this algorithm is completely generic. We can use it to sort any type. No matter what we have a list of, we can sort those things. We're going to take a list of values of that type. And we're going to take a comparator, which is a function which takes two of those types and returns a Boolean, which tells us the relative order of those two types. It's going to return true if the first value should come before the second value in the fully sorted order, and false otherwise. As long as our comparator follows that and whoever's calling this thing gives us a valid comparator, merge sort is going to sort this list and return a new list with those values in the sorted order. So we're going to have our check if the length is 1. I'm going to put less than 2. I usually do that just as a safety in case somebody gives me an empty list. I want to be able to return that empty list. So just a little bit of a failsafe. But from the recursive calls, we're actually never going to get a list of size 0. It's always going to be 1 for the base case. I like less than 1 just for safety, just in case somebody gives me an empty list. If the list is size 1, just return it. It's already sorted. No work to do, nothing to see here. Else, we're going to go into our recursive calls. We're going to split this thing in half. And just to condense the code on the slide and ignore the details that aren't really relevant to the recursion, I'm going to call this internal split at method. It's a list method, a method from the list class. I'm going to split it at a point that's going to return 2 lists. And yes, you can return 2 return values in Scala. It's not something we'll do in assignments. This is not something I'll make you do, but we can use that to our advantage with the built-in methods. And it's not that hard to do. It's just there's enough in this course already. It would just be one extra thing. So we're going to split at that index, get a left and right half of this list. And notable, I'm using integer division here. This is a case where I do want integer division. I don't want to retain any decimals. If the length is 3, I don't want mid to be 1.5. So I'm purposely using integer division here so that takes the floor of it, and then mid would be 1 if the length is 3. So I'm taking advantage of that, splitting at that midpoint. The extra element goes to the right if it's odd. And then magic, recursion. Which recursion, hopefully in these next 2 lectures, I'll dispel some of the mystery. But right now it probably does feel like magic to you. If it does feel like that, don't worry, you are right on track of where you're supposed to be. If you're like, wait, we're calling this method merge sort, which is currently being called. So we have a call to merge sort on the stack, and that call to merge sort is going to put another call to merge sort on the stack, which is going to put another call to merge sort on the stack. And then suddenly the list is sorted. It's crazy. It's witchcraft. Yeah, exactly. Jesse Gal. It's freaking witchcraft. It's crazy. It's something that takes a long time to digest, a long time to really understand what's happening with merge sort. And I highly recommend, we'll do some of it on Friday, hopefully a little bit today in the debugger. But actually watch all the frames go on the stack and visualize what happens on the stack. And of course, for your lab for this learning objective, you'll have to draw out the stack and heap and tell me, just like on learning objective 1, what's going on. Here's a recursive method. When it's called, what's happening on the stack is going to be a big part of these. So I recommend getting practice with that, because writing this out on the stack or watching it in the debugger and seeing what's happening on the stack can really help you understand what the heck is going on with these recursive calls. So we make these recursive calls. By magic, we have the left and right half both sorted, and then we're going to merge them together. And again, the details of merge, we'll talk about that after we talk about merge sort, this algorithm directly. But this is the whole algorithm. This is how we sort. There's details hidden in merge, but this is it. If it's length 1, return it. If it's greater than 1, split it in half. Recursively call sort on each half, and then merge the two halves. Recursion is kind of an advanced loop. It's a good way of thinking about it. So let's talk about the runtime quick. You'll look through this runtime proof more in depth when you get to 250. So I want to give you just the TLDR of it. So we have a list of size n, and then each level of the recursion, we're going to split the list in half. And we're also going to half the size of the list, and we're also going to double the number of lists that we have. So for each layer of the recursion, we think of it as layer I. We have 2 to the I lists of size 2 to the I, n over 2 to the I. So the first iteration, when I is 0, we just called this thing n over 1. N, we have 1 list. 2 to the 0 is 1. We have 1 list of size n. Once I is 1, we go to the next level of recursion. We have 2 lists of size n over 2, then 4 lists of size n over 4, 8 lists of size n over 8, so on, so forth. So when do we stop? When do we get to the end of the recursion? Well, that's when the size of our list is 1. So when n over 2 to the I is 1, that's when our recursion ends. That means we've reached the last layer of our recursion. And if we solve for I, that's at layer log of n. So we have log of n layers to this recursion. Log of n frames are going to end up going on the stack in this recursion at one time. That's the depth of the recursion, because we don't put all of the frames on the stack at the same time. We should be able to get to the debugger and see that. So we have log n levels, and each level has to merge a total of n elements. It might be merging 100 lists of size 2 if n is 100, but total we have to merge n elements across all of the recursive calls. So if we can merge in linear time, we'll end up having an n log n total runtime. So that's the really quick kind of hand-wavy proof of this runtime or runtime analysis. Again, more details in 250, where you'll get more mathematically thorough and proper with the proof. But that's what kind of my quick and dirty, this is the proof. Log n layers, if we can do O of n time each layer, n log n. So we need to merge 2 sorted lists of O of n time. That's our goal here. And very importantly, we have to take advantage of the fact that these lists are sorted. If the lists were not sorted, if our goal is to merge 2 unsorted lists in O of n time, that's the same thing as sorting in general. So if we could merge 2 unsorted lists into 1 sorted list in O of n time, well, the first thing we could do is just combine those 2 lists together and then sort them. If we had a way to do that, we would just use that as our sorting algorithm directly. So we have to take advantage of this structure that we have, that the lists are already sorted. So to do that, we're going to start, our merge is going to start with pointers to the first element of each list. Compare those two values. Whichever value is less, add that to a list that you're going to return, the full sorted list, and then advance that pointer. Repeat until you reach the end of one of the lists. Once you reach the end of one of the lists, copy everything from the other list over. And notice that when we do this, every time we make a single comparison, we're going to get one element into the final sorted list, which is going to give us the linear runtime. We're going to do constant amount of work for each element that we copy to the return list. So we're going to get an O of n total runtime of this. Alphonse, I mean, thanks P, but how does that help me right now? Alphonse had a good explanation about merge sort in 115. I don't disagree. I mean, he's been doing this a long time. I'm sure he has great ways of explaining most things, probably better ways than I do. We do have the videos linked in the syllabus. If you go to the 115 review, you can go get Professor Alphonse's explanation. If mine doesn't make sense, go check out his. Go search online. Get as many different voices as you can to understand this stuff. Yeah, if he has a great one, go watch it. So we're going to start with pointers at the first element of each list. We're going to compare. 1 comes before 2. Assuming we're using less than, the less than operator for our comparator. 1 comes before 2. Copy 1 into the output list and advance that pointer. Compare these two. 2 comes before 9. Copy that one over and advance that pointer. And as we're doing this, this one isn't too much magic, but the trick comes in to the fact that we're taking advantage of transitivity. We see that 3 comes before 19, and we know this list is sorted already. So if 3 comes before 19, according to our less than comparator, and 19, and this list is sorted, therefore 19 must come before everything that comes after it in the list, then 3 must come before everything else in this list, from 19 onward. So with 3, with our inefficient sorting algorithms, we would be comparing 3 with 4, 8, 2, 100, 51, 19. We'd be comparing it to all these values, but we're taking advantage of the fact that 19 was already compared with these values, either directly or indirectly, and then making one comparison and gaining a lot of information from that single comparison. So 3 compared with 9, copy 3 over, go to 4. 4 compared with 19, copy 4 over. 8 compared with 19, copy 8 over. We've reached the end of one of the lists, so now we just copy everything else over. Everything else just gets dumped into the output list because we know this is already sorted and there's nothing else to compare to. Nothing else to do, copy the list over. Dr. Alphonse hasn't done 250 in since I was an undergrad. I don't know if he's ever done it, to be honest. But at least not since I was an undergrad. Back in 2008. I don't believe he's ever taught it since then, at the very least. So that's how we're merging in linear time when the two lists are already sorted. So let's look at the code for this. The code is a little bloated here, but a lot of it's kind of duplicated. There's no super easy way to get rid of the duplication because we have the left and right side. And still make the code readable, legible, I guess. So we're going to initialize our pointers to 0 for the right and left lists. We're going to take our same comparator that merge sort had. We're going to initialize the sorted lists. And then each time, as long as we're not at the end of one of the lists, we're going to use a while loop, something we don't talk about enough. There's a lot of cases where a while loop is handy. But in 115, we kind of introduce it, but don't really talk about it too much for reasons, good reasons. But this is a handy case where a while loop is much more useful than a for loop. And for your like alliterations lecture question, if you're still working on that one, a while loop with this setup, initialize your pointers to the beginning of the first character to the index 0 of each list, or the first sound of each list, and then use a while loop to iterate through both of them at the same time, well, or actually you only need one pointer for that one, but using a while loop, while these sounds are still the same, keep going through the indices, and then after that while loop breaks, after they're not the same or we reach the end of one of the lists, return the index that we made it to. So that's another case where while loops come in handy when you need to iterate over multiple data structures, or you need to not iterate over all of the data. There are cases where while loops are handy, or you're just not iterating over data at all. Or you can use zip. A lot of people use zip for that. So while we haven't reached the end of one of these lists, use our comparator, which again, we don't care what we're sorting or how we're sorting it. We're just going to call this comparator, this first order function, and check each element that we're pointing to, and if the left comes before the right, we're going to append that value to the end of our sorted list and increment our left pointer by 1. If the right value comes before the left value, or there's a tie, we're not actually checking ties because we just don't care. We're going to let ties arbitrarily be broken by the right list. Then do the same thing over there. Append the value that the right pointer is pointing at to the sorted list, and then advance that pointer. Once we reach the end of one of these lists, check which list we've reached the end of, and then append everything else in that list over to the sorted lists. And again, using a while loop, I just want to keep doing this until we reach the end of the list. But I'm not iterating over all the data, so I can't just say 4 values in left or 4 values in right, because I already copied some of those values over, and I don't want to recopy those. So I'm just going to use another while loop. Well, the pointer's not at the end, just go through and copy everything over. Oh, my homies hate loops? What? Loops are the best. But if they do hate loops, then they must have loved Calculator and Microwave. Or are still loving. It's still out. So we just use this comparator the whole time. Oh, oops, we're very slow. Apply, very slow. Oops, append, also very slow. We'll talk about why append is very slow as well. So we actually don't get, with this specific implementation, we don't get our n log n, but I want to show the recursion and stuff. So we actually don't get our n log n. It should be n squared log n, and I think there's some magic in the math that ends up being an n squared algorithm. I forget the exact explanation. I don't feel like going through it right now because it's not relevant. But I believe it washes out, the log n washes out and ends up being n squared runtime for this specific implementation. So we actually did, we did worse than selection sort, the same asymptotically. But and also, I banned var. Hopefully some of you are upset by this. I banned var and then used it in my dang example. And I said I wasn't going to use var at all for the rest of the week. So what the crap, professor? So here's my version that doesn't use var. So I got to at least show this because it's not right for me to show you an example with var. I showed you the example with var because I want to make sure that we all understand what merge is doing. And here's the version without var, which might be a little less readable. But I will argue as we talk about more functional programming techniques, I will argue that our code gets more expressive. There's a lot more we can express in fewer lines of code, even though those lines of code might be more difficult to read, and we have to use more features of the language to be able to get that code done. So here's my no var version of this. Since I'm tempted to use a loop here, I'm going to change that loop into recursion and use recursion as kind of as my loop, as someone in chat mentioned earlier. So my no var merge method that takes a left, a right, and a comparator, I'm going to rewrite this with recursion, and I'm going to use an accumulator variable, which is going to accumulate the results that I want as I go down the recursion. And this is a common thing that we do with recursive algorithms. We have some public interface. Somebody wants to merge 2 lists that are already sorted with some comparator. I'm going to give this method to them. And then all this method is going to do is defer to a recursive method that does the same thing, but has some accumulator variable as one of the parameters, which is going to collect all the results from the recursive calls. So I'm just going to defer to my recursive thing, without having to tell everybody, hey, this algorithm, give it an empty list as its first parameter. And we don't want to do that. So we're going to give it the accumulator, initialize it as the empty list, and collect all our results there, and then do a few checks. If the left is empty, I'm going to take everything in the accumulator, which should store all of the results that we found so far, and append the right list to it. I'm reversing just for some efficiency that we might talk about. I'll talk about that more when we get to linked list as well, but I'll give enough for you to know why we're doing that right here. The accumulator, the triple colon is going to combine. I saw that question in chat. That triple colon is going to combine two lists. So I have a list here, an accumulator, and a list for right. If I want to append a single element, I use two colons. If I want to combine two lists into a new list containing all of those elements, triple colon. It's another method of the list class. If the right list is empty, same thing, accumulator, but append the left list. And my recursive calls, if I'm not at the end of one of these two lists, I'm going to call my comparator on the first element of each list. And if the left value should come before the right, I'm going to make a recursive call with that left element prepended to the beginning of my accumulator, which is storing all of the values that are in the final sorted order. And I'm going to append this in reverse order. Prepend, the reason we're doing this, prepend is much more efficient than append. So I'm prepending to the accumulator and then handling that in my base case by reversing that into the right order and then appending the other list. So I'm accumulating in reverse order and then reversing them in my base cases. And then I'm going to give the recursive call the left list, but I'm going to drop the leftmost element. So drop 1 returns a new list with the first element of that list removed. So this is going to be a new list with the first element removed. Then make the recursive call until one of these lists is empty. We already dropped all of the elements, got to the end of the list. Right list is unchanged, comparator unchanged. If the element that I'm looking at the left didn't come before the right, so right comes first or a tie, do the same thing with the right list, just reverse everything. Append the element that the right list we're looking at to the final sorted order and drop that from the list. So this is our no var solution. So anybody who's complaining, if you were thinking it, which you should have been, I would have been, hey, I can't use var in my lecture question, but you use it in your slides. Here's your no var version of merge. All right, so you need to start writing recursive methods. At this point, you should be able to follow a recursive method or function, at least to an extent. You should be somewhat getting comfortable with that. Looking at a recursive function and following what it's doing and convincing yourself that it does work, even if you don't fully understand why it works. But now we need to start moving into how do you write recursive methods? How do you come up with your own? You have a problem that you need to solve. How do you come up with it? And here's my suggested approach. Break it down into these steps and follow this as kind of formula for writing recursive functions. First, assume your recursive calls are correct. The very first thing I recommend you do is just get past the point, get it in your head that you can just assume that the method that you're currently writing already works. That's where the magic happens. Just assume that it already works. It's going to work when you're done, right? Your goal is to get it to work, right? So just assume that it already works. Assume your method works. Write your method based on that assumption. So assuming that it works, leverage that fact. Whenever I make a call, if I want to make a recursive call to my own method, I'm just going to assume it works and assume that it returned the right value by the magic of recursion. Just assume it works. Base all your logic on that assumption. Write the whole algorithm and just assume that it does work. Add a base case for an input that has a trivial return value, so anything that you just know the answer to. In merge sort, this was a list with one element. It's already sorted, done. With merging, it was we've already reached the end of one of these lists, and then I can just combine two lists and be done with it. Some case where you know the return value and you literally can't mess it up. You just know the return value. And then the last ingredient to this formula, make sure every recursive call you write gets you closer to the base case. If you miss this one, you're going to get the infinite recursion, the stack overflows, infinite frames on the stack until you run out of stack space. Make sure you always get closer to your base case. If you follow these 4 steps, you got a good recipe for success for writing a awesome recursive function or method. Dan, could you run through this with an example? This part that I'm how to write a recursive method on, I won't have time, but on Friday, that's what Friday's goal is. And I'll show merge sort. I'll show the example of merge sort. So I'm going to assume writing merge sort, designing this thing. I'm going to assume my recursive calls are correct and design an algorithm based on that assumption. So if my recursive calls are correct, I can split the values in half, split this list in half, and then recursively call on each half, and then merge those 2 halves. Since I'm assuming merge sort works, I can get away with this. I'm just going to assume it works and call it, and assume that merge sort returns sorted lists, and then I'm going to merge those sorted lists. Add a base case for some trivial output. If the input is either empty list or a list containing one element, just return it. The base case is always some very trivial, it can't go wrong type of input. If I get a list that's already sorted, it's already, one element's already sorted, return it. And then only write recursive calls that get closer to my base case. So when we're just on this first assumption, I can't just say merge sort, just call merge sort on the entire input data and call it a day. I have to make sure my recursive calls are getting closer to my base case, and I'm doing that by splitting the list in half. So if I have a list of size n, no matter what n is, some positive integer, no matter what n is, if I divide it by 2, I'm going to get closer to a list of size 1. So every time I make a recursive call, I'm getting closer and closer to this base case. And once I hit the base case, then the recursion can stop and start returning. We're no longer adding more frames to the stack once we hit the base case. Now we get to start returning values and start removing frames from the stack and start going back up the recursive calls, going back up the stack and returning values. So we have to make sure we're hitting our base case, hitting that trivial input-output behavior, and then the rest of the magic can work, and all of this can come together and just make things happen. I don't want to go through all of these one at a time because I just explained these. I do want to get to some IntelliJ. Those slides were just explaining what I just explained, repeating myself more and more. So here's my window. So let's take a look at some of these examples. So first, for runtime, when we just had selection sort, I want to run my selection sort code. Oh, face, good call. So I want to run my selection sort code. And this code is going to run the algorithm. I have some timing code here. I'm going to sort by absolute value, generate a random list of size n, give it that list of size n, and for now I'm going to print out just to prove that this is working. I have 20 random doubles from negative 0.5 to 0.5, and we're sorting them by absolute value. So just to prove a concept that just to prove that it does work. Oh, and decreasing order of absolute value, of course. greater than, and I'm taking the absolute value of each. So just to prove that we are sorting correctly. And then I want to look at the runtime. This took 10 milliseconds to sort 20 elements using selection sort. Let's move that to 238 elements. And at this point, I want to stop printing out the list each time. We got the idea. We're sorting properly. For 200 elements, I didn't even change anything. For 2,000 elements, now we're starting to feel the pain of n cubed in this case. We're already at 4.6 seconds, and if I go beyond 2,000, it's going to start, slowing down lecture quite a bit. This is getting pretty bad at 2,000. When we go to merge sort, let's start at 2,000, and I gotta double check which one I'm using. Merge sort with merge. Okay, so this is the first merge method that we saw. Oh my goodness, where is it? This is the first merge method that we saw, the one that's more readable, the one that has append and apply, horribly inefficient algorithms or implementations. But let's run this on 2000, see if we can at least reach 4.6. And we do 1.92 or 0.192, which asymptotically we should be about the same as, oh my goodness, same as merge sort. There's my print line. But realistically, we are a lot faster than them. And we can see proof that this is working. We do get these values in sorted order. So I'm going to remove our print line here. Let's move this to 20,000. And we're really starting to feel that n squared at this point. It's chugging along quite slowly. So while that's thinking, 10 seconds. Let's go to, do I want to do foreshadow merge? I didn't talk about it. Let's go to no var merge, because I did implement that efficiently. I only used prepend, not append, and I didn't use any applies in there. I only asked for the first element, which is fast. So same input size. Run this. And it's sorted. 89 milliseconds. This is the difference between n squared and n log n. With n squared, we beat the other algorithm because I have my n cubed implementation. That's why the bad merge sort was so much better than selection sort, because I have an n cubed. But now, once we're up to 20,000, and let's go up to 200,000, the difference between n squared, which was that first merge sort we saw, and n log n is ridiculous. Let's go up to 1,000,000. That took half a second. Let's go up to 1,000,000 elements, because why not? We're starting to feel it a little bit, but 2.5 seconds to sort 1,000,000 elements using a custom comparator, not too bad. And there's one more sort I want to show. If I use sort with the same comparator, what do we expect the runtime to be? Well, I hope it's faster than mine. But since they're asymptotically the same, we're not going to get a ridiculous increase. It was, about more than 2.5 times, maybe about 3 times faster, but we're not getting a ridiculous increase from that efficiency. We are going to get an increase because the sort with method, the built-in sorting methods of any language, including Scala, have been developed over decades by teams of developers trying to squeeze every little bit of implementation out of this, every little bit of efficiency out of this algorithm. So this is going to be a very, very efficient algorithm, which my algorithm that I slapped together in less than an hour for a lecture example, that's meant to be legible and not efficient, even though it's not terrible. It has the same asymptotic runtime, but that constant, a factor of 3. We can live with that, but if you're ever really needing sorted things, use the built-in methods for each language. But this should be timsort, which was being mentioned in chat on Monday. I don't know if I'll be able to find it, though. But anyway, it uses a more advanced algorithm, of course, and all kinds of fancy stuff. So the last thing I want to talk about, I guess this won't really technically be in lecture proper, depending on what you want to consider part of lecture. But this example will certainly help emphasize this point. I want to get through that runtime faster than I did. But let's need it right here. But let's run this debugger. And I highly, highly recommend, I can't recommend this enough, do this yourself. Run, go in the repo and run the debugger on these examples to see what's happening, especially in these recursive calls. So with this, we're going to hit this merge sort. We have main stack frame, which is just going to call large example. My large example method, which just sets up the random list. So we have a list of random values that we want to sort. And then calls merge sort. And then merge sort, we're going to put that stack on the frame with an input of all 10 elements. And the comparator, whenever you see this at 1018, we can show that this comparator is on the heap. The linked list, all the elements are on the heap. All the stuff's on the heap for what it's worth. And then we can start going through the algorithm. The input is size 11. So we're going to hit our recursive call. We're going to split this into 2 lists, left and right, each with half of the elements, with the extra element going to the right if we have an odd size. And then call merge sort on the left list. This is going to put a new frame on the stack with just that left list. The input size is 5, so we're going to go to a recursive call. We're going to split this into its left and right lists of size 2 and 3, and then call merge sort on the left list. Size is not less than 2. Split that into 2 lists of size 1. Make the recursive call on the left side, which is just a list of size 1. So we hit our base case. At this point, we have 4 different frames on the stack for our recursive call. We have the initial call with a list of size 11, which is waiting for its return value of merge sort of the left list. That call split the list again and is waiting for its return value of the left list, which made a recursive call and is waiting for its return value of the left list, which is not making a recursive call, which can finally return and start destroying stack frames and going back up the recursion. So this is going to return the list that it was given. Yeah, why would it go down there? It's just hitting the end of the else, but that doesn't make sense. We don't need to go there. So this stack frame with the 2 lists of size 1 just got the return value of the left list. So left sorted is going to go on the stack. We have left sorted on the bottom of the stack, and it is just the list of the left values sorted. Then we make the recursive call to the right side. That's just 1 element. I don't know why the debugger even thinks about that code. That stack frame is destroyed and returns right sorted. Its return value is assigned to right sorted. So we have the left sorted, the right sorted, and we can call our merge, which calls our merge helper. So now this stack frame is waiting for the return value of novar merge, which is waiting for the return value of novar merge helper, which is going to be computing on these 2 lists. We have to merge this left and right, these 2 lists. Neither of them are empty. So we're going to make a comparison, call our comparator that we have, that we were given. So we went to the heap, found that comparator, applied that function, got our return value, and it must have been false because we're going to the else. Making another recursive call. This, I actually meant to rearrange this algorithm, but we actually don't put a new frame on the stack here. You should assume for your quizzes, actually I'm just never going to give you something like this on the quizzes, but this is what we call tail recursion. So the compiler is smart enough to flatten out the recursion and not put a new frame on the stack here. But we would put a new frame on the stack, and here our right list is empty, append left list to it, and then return. Return. So those stack frames are gone, and this step of the recursion can return that list of size 2 that was merged together to this stack frame, which was waiting for that return call. So now we have left sorted with these two values in sorted order. Remember, we're sorting by decreasing absolute value, so this is the correct order, 0.4 to 0.2-ish. And then make the recursive calls on the right side. So now we'll go to the right side, make those recursive calls. This is a list of size 3. Split it. Get a list of size 1 and 2. Sort the left. Nothing to sort. Sort the right. That's a list of size 2, so split it. Recursive call to the left. Recursive call to the right. They're sorted. Merge them. Return, and now we have a list of size 1 that's sorted, a list of size 2 that's sorted, and we actually have some merging to do. I'm going to skip through some of the merging, especially because it doesn't put more frames on the stack. And now we have one more. And now we have, and this is where I'll stop it, but hey, how come I'm still, oh, I think I jumped a little too far there. Got a little too click happy. I have a breakpoint there. I see, because I had an extra breakpoint. But oh well, we got farther than I wanted to, but this is a better example anyway. Happy accident. So now when we get to that top level call, when we finally have merge sort returning for the left and right lists, we have the left list sorted, we have the right list sorted, and then our task is to merge those two lists. So there's no magic, like no step there, you know, except where I got a little click happy and started going pretty fast. But no steps when you go through the debugger. None of those steps are magical. You'll see that there's no magic there. And when you go through the debugger and check it out like that, it can really show you what's happening, and you can start thinking about where it appears to be magic, start dispelling that magic, and then understand recursion. So let me set a breakpoint at the base case. Just to emphasize this one more time. I'm going to set that at the base case, and we're going to go 1,000,000. What do you think is going to happen here? Restart the debugger. So we get a lot of frames on the stack, but only 20 calls to merge sort with 1,000,000 input. And I like to show this just to show the power of exponentiation in logarithms. So we started with an input of size 1,000,001. Split those lists in half, recursively call on the left side on 500,000, recursively call on the left side 250,000, 125,000, 62.5 thousand, 31,000, 15,000, 8,000-ish, 4,000-ish, 2,000-ish, 1,000-ish, and you can see how fast the numbers decrease when you're halving each time. It only takes 20 halves, half a million, 20 times to get down to 1, which 2 to the 20, it's a little more than 1,000,000. You can run the numbers, you can play with your calculator, figure that out, and verify yourself that it only takes 20 doubles. So 2 to the 20 is roughly 1,000,000. So the log base 2 of 1,000,000, it's only 20. So when we have that n log n, even when n is 1,000,000, it's like 1,000,000 times 20. So like 20 million steps. It's not too much crazier than just straight up linear. And if we go up to 1,000,000,000, I'm not going to do it here, but you know what? I will. If we go up to 1,000,000,000, how many frames are going to be on the stack when we reach the base case for the first time? How long does it take to go from 1,000,000,000 to 1? Let's see if it does, if we do get there. We should. We don't actually do any merging here. It should actually go really fast. Oh, you know what? Because I have to generate a list of size 1,000,000,000. That's what's going to take a while. I might even hit swap space on that. This is going to be our bottleneck, just generating the thing. But the recursive calls should go really fast if we can get there. What's yeah, but 1,000,000,000 ints, 32-bit ints, or these are doubles, 64-bit doubles. Yeah, I'm gonna fill up RAM and be hitting the ceiling there. So let's go to 100 million. Yeah, my RAM isn't gonna like that one at all. Oh, yeah, I should have downloaded more RAM right before lecture. Thanks, P. All right, and now we're definitely just chatting. So if I had more time in lecture, that's what I would have gone through. If people left at 2:40, that's fine. But for those of you who wanted to see it, I wanted to make sure I went through that. Yeah, 2 to the 20 is just a little bit more than 1,000,000. So 1,000,000,000, if that 1,000,000,000 ran, it would have been 30 stacks, 30 frames on the stack. For every order of magnitude of 3 zeros is a rough rule of thumb. Every 3 zeros that you append in base 10 is another 10 powers of 2. So 1,000 is roughly 2 to the 10. 1,000,000 is roughly 2 to the 20. Billion roughly 2 to the 30. Trillion is roughly 2 to the 40, and so on. So every time you go up an order of magnitude in base 10 like that. Looks like even 100 million, we're not quite getting there. Unless I have an extra 0 in there. I might still be, especially since I didn't kill that gracefully, my machine might be still figuring out what to do with RAM. How much memory do I have on that computer? I don't remember. I think it's 16 gigs, but I could be wrong. Enough that it's usually not a problem unless I do something silly like this. How can we see the developer's code? Oh, so I control click on stuff. Control click, and it goes into the library. It goes to that definition. You can also do this in your own code. So like if I'm in merge sort and I'm using novar merge and I want to go to its definition, control click, and it's going to take me to novar merge. Control click that. And if I want to see like what does reverse do, it's still going to take me to that code, but since I have all the code, all the Scala standard library on my machine, it's going to take me to that code as well. Which also, when you do Maven, I always recommend making sure you're downloading sources and documentation, because then if you're using a library that you've installed with Maven, you can do the same thing. You can go into that library and take a look at the code. But if you don't download the source and the documentation, you might, if you just download the source, you're just looking at code with no comments, kind of like this. And if you don't download either, you might just be getting the compiled code, the Java byte code for the library, and then you can't look at either. Yeah, this thing. I think I broke the example. What about Tomorrow Lab? What kind of... Tomorrow's Lab is LO2 verification. What about it? This, oh, you want to see the random code? Yeah, there's no such thing as true random, if that's what you're talking about. I won't study. There's no such thing as true random. It's all RNG, random number generators. Was that my problem as I ran it? Oh my goodness. Is that really what I did? I ran it instead of running in the debugger? Come on. Well, 10 million took some time there. We'll get this. I'm determined now. I want to see this stack. 2 minutes. We can do this. The default random, the random function I'm using, the random method in math, it gives you a random double from 0 to 1.0. So I wanted to just shift this range. I just shifted it by 0.5, so I have negative and positive values. If I wanted to, let's say I wanted values from negative 10 to 10, I would just multiply this. Where am I? I would just multiply this by 20. And now I have random values from negative 10 to 10. Well, I'm not that determined because it's 4 to 42 time. Oh. I don't even have slides. So next Friday, I can't believe we're at the halfway point already. But one last 116 thing. Next Friday, I'll come up with something good here. Maybe we'll just do examples or review or catch up. But I actually scrapped my lecture last semester because this was the one right before spring break. This is when we went to online only for the first time, so it's memorable to me. I canceled the lecture. I canceled the lecture question and everything, and just had it like a heart-to-heart with the class and said, we're all in for a journey here. So it's kind of memorable that now we have that lecture. It's been a full semester online only, starting Friday.